Okay, welcome to this class. We were reach a point of describing a number of industrial robots in different applications. We have seen that those robots change in structure. There are different articulated bodies moving in the workspace. But we can characterize a few typical structures, classes of articulated manipulator. And in particular, we will refer in the following parts of the course to one main structure, which is the one shown on your left side. For instance, for a KUKA 150 robot. And we refer to this arrangement as an open kinematic chain. Underlying is we assume that we have a chain of rigid bodies that we will call links, connected by elementary joints, which will be only of two possible types, revolute or prismatic. Revolute joints provide a rotary motion of the link following the joint with respect to the link before the joint, while prismatic joints provide a linear motion to the following link with respect to the link before the joint. Even if we have a very complex articulation, we can always decompose this in elementary joints. The characteristic of this class of manipulator is that there is a serial sequence of joints and links. In this sense, we call them we denote them as having an open kinematic chain structure. So we can start from the base, and then we have the first joint, and then we have the first link, the second joint, the second link, and so on until we reach the end effector. So we will have in general n joints. Typically n is equal to 6, but maybe any number, moving 6 rigid bodies, or n rigid bodies, if n is equal to 6 rigid bodies. And this is the most common situation, or I would say the easiest one to analyze. We have already seen some examples, and here is the situation in between, where we may have some closed kinematic loops within the mechanical structure. We already mentioned that one reason for having this loop, like the parallelogram that you see in the Italian robot Comau Smart H4, is due to the fact that we want to relocate the position of the actuators, typically electrical motors, close to the base while moving remotely driven links, so that we don't have to, the robot doesn't have to carry the own weight of the motors which are needed to move the links. So if these motors are relocated close to the base, they move relatively little, but they are able to move the remote links through the presence of this kind of articulation, in particular a parallelogram, and then we have a closed kinematic chain. For kinematic analysis, we will most of the time remove this path and assume an equivalent open kinematic chain structure to which we assign all the characteristics. We will see we will assign reference frame to each bodies and then connect the position and orientation of this frame with respect to the previous one in a serial way. However, there is another class of robots which are completely different. They cannot even be approximated by open kinematic chain by removing some closed kinematic loops. And these are the so-called robots with parallel kinematics. And here you see one Japanese example, a Fanuc. And this type of kinematics is also often called Stewart platform. In this case, we have joints, which you can see here in this type of legs. These are purely prismatic joints, so they extend or compress. And there are 6 of them. And by the relative motion of the 6 prismatic joints, the platform which is on top will change position and orientation. As strange as it may seem, the mobility of the top platform, which is the end effector of this robot with parallel kinematics, is exactly equivalent to the mobility of the end effector of the 6 degrees of freedom serial manipulator that you see on the left. With the 6 joints of that arm, we can position and orient in a restricted workspace the end effector of the KUKA arm. In the same way, with the 6th joint of this parallel kinematics, we can move around and reorient the end effector of this parallel kinematic robot. Okay? Having said this, we will not cover this class of robots, although it's important. I want just to mention a few differences in handling these 2 cases, and I will help myself with a drawing on the blackboard. So forgive me for the bad drawing, but on the left we have a sequence of joints and body, which I can represent like this. I'm starting from the floor, from the basement, and I have revolute joints. Here is the base rotating, here is the shoulder, the elbow, whatever. Okay? So, for what I want to say, I will define 2 reference frames. One at the base of this serial manipulator. So this is a serial kinematics. And we will consider mostly this case. So I put a frame which will be a reference frame at the base. Let's call it reference frame 0. So it will have axis x0, y0, and z0. And we will refer all position, all orientation, all motion of the robot with respect to this particular base frame, which is fixed in the world if the robot has a fixed base. If the robot is mounted on a mobile base, this frame will move depending on how the base of the this mobile robot will move around the world. Okay. The other important thing is to place some frame, which I will call reference frame E. E stands for end effector. So this is base, and this is end effector. Again, there will be an X, a Y, and a Z axis. All frames that we will consider are right-handed frame, so they obey the right-hand rule. X, Y, the vector product of X and Y gives the Z direction. Okay? So, the mapping that given a set of variables that describe the angle of each joint, and we will see how to use a systematic way for defining this, the mapping that characterizes the position and orientation of the end effector frame with respect to the base frame is called direct kinematics. Okay? So if I'm assigning a value for Q1, Q2, let's say Q6. Suppose that we have 6 joints, and Q1, Q6 are angles characterizing the values of these joints, then I can compute position and orientation of the end effector, and this is solving the direct kinematics. Now, this problem is easy. Once we have defined all the tools, once we have uniquely characterized the specific kinematics of a robot, we can solve this by product of matrices, essentially. And there is only one solution, okay? And there's always a solution existing. Now, the inverse problem inverse kinematics problem is more or less stated in this way. I would like to have, for the end effector frame, a certain position and orientation in space. Of course, assume that this is not very far away and there are no special cases to consider, so it's a generic good position within the workspace of this robot. So, given this desired pose of the end effector, what should be the values of the angles that realize this pose? Well, this is not at all a trivial problem, as we already mentioned in the introductory lecture with some highlights. And in fact, this is a difficult problem. Difficult but not unsolvable. There are cases where we can find an explicit form for all possible solutions. We can classify also singular situations where the number of solutions is not regular. They may increase, become infinite, or they can decrease in number. Instead of having, let's say, 4 inverse kinematic solutions, we may have only 2 or only 1, or we may not have any if we have taken a position which is too far away from the base. Okay, so we will see how to solve when we can be assured that there is a solution, when we don't know how to find this closed form solution, and resort to some numerical algorithm for finding at least one inverse kinematic solution. Okay? And this is one side of the story. Now assume the extreme other case. So not serial kinematic, not even mixed serial closed kinematic chains or so, but fully parallel kinematics. And now things get worse for my drawing. So suppose that there's a base, and then mimicking this drawing here, I can have pairs of prismatic joints, and then there's a top plate here, and at each corner I have a pair of prismatic joints connected to the base. More or less. It's not really. You may wonder, what kind of joints do we have here at the base and at the top? These are called passive universal joints. It's like having a ball moving inside another ball and having the possibility of assuming any orientation, pointing, and so on. So these are passive, completely passive. There is no actuation. The only actuation extend or retract the legs of this Stewart platform. By the way, this type of structure is found in several contexts, even beyond robotics. For instance, emulator of flight are cockpit room where pilots enter and have all the electronic commands, and then can emulate the flight, including dynamic effects. So this cockpit is on top of a huge steward platform and will be moved around, accelerator left, right, up and down, rotated, and so on, as if following the commands that the pilot is giving. So to give a more realistic feeling of flying an airplane. And of course, inside this cockpit, you have some kind of virtual representation of the outdoor, and so on and so on. Okay? So, in this case, we do the same. We have a base frame placed on the bottom plate. So this is reference frame 0. And on the top frame, on the top plate, sorry, there's a reference frame and effector. Exactly the same problem like this. And the value of this extended legs, Q1 to Q6, characterize the configuration of this robot. Exactly in the same way as the angle that we do around the joint axis for this serial kinematic chain. Okay? Now, we can pose ourselves the same problem. So if I'm giving values to this Q1, Q6, can I compute the direct kinematics and characterize position and orientation of the end effector frame? Yes, I can. And vice versa, if I want to realize some desired position and orientation of the end effector frame, what should be the value of the joint variable, in this case, this linear extension of the prismatic joint? Okay? So, same problem posed as for serial kinematic chains. The intriguing thing is that inverse kinematics is easy. And in fact, we can find a closed form solution quite easily. Because the problem is of the type divide and conquer. So we can separate the problem of finding the values of the joint variable Q1 to Q6 in independent problems. While the direct kinematic is difficult. Sometimes it has no solution. Why? Imagine that you assign some large, very large value to Q1. Then there will be no other value of Q2 to Q6 that are able to satisfy the constraint, the physical constraint that these legs should end always at the same point on the upper plate. So you have a kinematic constraint, which is of the form of a closed chain, in fact, but it's all closed. There is little serial or no serial at all in this structure. And so you may not even have a solution for the direct kinematic, and you may not even have a closed form solution. So it's exactly the reverse situation as for serial arm, and in fact is insofar that the inverse kinematic is easy. And you may convince yourself with a bit of intuition in this simple case, because if I'm assigning the position of this frame and its orientation, since this frame is attached to the top plate, then I can also characterize this anchoring point for this pair of legs. Now, I know the position of this point, the desired one. I know where is this base, and this is a fixed value with respect to the base frame. And now I have 2 points in space, and I have to compute the distance between 2 points. And this is the value of the joint variable. And I can repeat this for all 6 legs. And I'm done. Okay? So you can see that it's obvious that you have a solution. In fact, you can find a solution with close analytic expression of the data of your problem. The data in this case are position and orientation of this frame. Okay? So it's very important that we are able to distinguish these two cases. With this in mind, many of the techniques that we will see for serial manipulators can be dualized in a sense and applied for the problem of direct and inverse kinematics. But having said this, we will leave this situation on the side and focus on the large majority of robots kinematics which have this open kinematic structure. And if there are, in fact, there are often some closed kinematic chain, from the kinematic point of view, we will remove the closed chain and handle the robot as if it's purely serial. And at the end, we will impose some limits on the joints because of the physical presence of this closed kinematic loop. Okay? You have question on this? Okay. Then we have seen in the brief history that we have developed last time that at some point people started designing some very special cases of serial manipulator, in fact, which are called SCARA. And here is the acronym, the meaning of the acronym: Selective Compliant Arms for Robotic Assembly. And they are typically robots of the serial kinematic type, so it's a special case, with 4 degrees of freedom. Remember, every joint, which is either revolute or prismatic, provide 1 degree of freedom to the structure. So we often confuse this concept, which is more general in mechanics of degrees of freedom, with numbers of joints, just because we handle only the case of elementary joints that provides 1 degree of freedom. So 4 degrees of freedom means 4 joints. And in all the SCARA family, and here you see a few examples, 2 Mitsubishi Japanese SCARAs, 1 German robot of the SCARA type produced by Bosch. They all have this full sequence of joints. There are 3 revolute and 1 prismatic. But in fact, if we start from the base, we will find first a revolute joint, the shoulder, then a second revolute joint, the elbow, then a prismatic joint that I cannot show you, goes up and down, and finally a 4th joint for rolling around this vertical direction, rolling the gripper in order to pick parts in the proper orientation on the plane. Pick them up, moving them, and then placing them down. Okay? So this is another class that is fully within this, but deserves some special consideration. Of course, if you think about now, this structure has 4 degrees of freedom. No matter how I move the 4 joints, I will never realize a generic position and orientation for the object that is being held with the end effector. There are some orientations which are not feasible for this structure. Can you imagine which one? So within some restricted workspace, because this is what we are talking about, I can certainly position the end effector and the object rigidly, firmly held by the end effector where I want. But I can only change 1 parameter of the 3 that characterize the orientation. Because I can change an angle with respect to the vertical. But if I want to rotate along this axis or along this axis the object, there is no mobility provided by this robot. In fact, the robot has only 4 degrees of freedom rather than 6. So this is a limitation in mobility, but for the application for which this robot is designed, namely assembly and pick and place operation on a flat surface, this is not important. Okay, so in this case, the designer preferred to have a simpler structure that is not capable of general positioning and orienting of its end effector, but it's enough for solving a dedicated task, which is of paramount importance. Okay? And here I have a video. A video which is a commercial video, but it's very nice. I hope you can see this video, and if you don't see it properly, I can now at least switch off the lights. Huh? Maybe. This depends on the low power bulb that we have. You can download this video from the website and have it with a perfect view, or wait for the production of the video recording of this lecture, and again you will have there the correct view. Okay, so this is a SCARA robot produced by a US company which is called Adept. And this is the Adept Cobra i600, whatever name, but Cobra is the brand name. And they claim that this is the fastest SCARA robot, at least at the time was delivered. Okay, let's see how it moves, and pay attention in particular to the mobility of the links. Now, we should not be too much impressed by this robot. Now we look into their motion, their mobility, to understand what we should be able to describe in order to cover the analysis and the synthesis of motion for specific classes of robot. So this is how it looks like. So you see that the robot is moving the 2 upper links, and it's moving some metallic balls on this wooden plate. And now with a gripper, a metallic gripper, it's picking and placing quite rapidly, but not at its maximum speed yet, all the balls. You see, there are very elementary rest-to-rest motions. So start at rest, I pick up, move, 0 velocity, leave it, and go to the next ball. You may have noticed that the elbow is now in the right arm configuration, but there were some other motion where it has a left arm configuration. Let's just change configuration. It can do it without changing arm, but we call this 2 symmetric inverse kinematic solution for this class of robot, right hand and left hand inverse kinematic solution. Okay, and this is the result. Quite impressive, I would say. Okay. Now, there are other type of manipulators, and one should be able to understand if they belong to the serial class or to the parallel kinematics class. For instance, here you have a so-called gantry robot. Now, the gantry robot, it's kind of a big structure, and it has mobility along the x, y, and z axis. And at the end of the third axis, so the first three joints are of the prismatic type, there is a spherical wrist, typically. So there are three revolute joints with axes intersecting in a common point. So that the positioning of the end effector is made by the first three prismatic joints, and the orientation is made by the last three joints, which constitute a spherical wrist. Is this a parallel or a serial kinematics? No idea. Who wants to guess? Both. Both. Partly serial, partly. Why both?
The plate is parallel, but the end effector.
Okay, we may agree that the last three joints that gives orientation is a serial. We have left open the point of denoting what is the series in these three, because we know that we can rotate around this axis, around this axis, but which axis comes first, we don't know yet. This depends on how we will model this. But in fact, let's take out the spherical wrist because this is serial. Now what is left is the three prismatic joints. Let me make a draw here. Let's consider a sub-case of a gantry-type robot. Not three-dimensional, but two-dimensional, in a plane. How many of you have ever used a plotter? Nobody. Do you know what is a plotter? You can make nice drawing for civil engineering and projection in X, Y, Z plane and so on. But essentially, a plotter is a pen moved by a computer that can go in X, Y direction. Okay? So I can model this as one motion, one extension or contraction along one direction, Q1, and holding a second joint, and then placing this. So the position P, X, Y, with respect to some X0, Y0 reference frame, can be changed by varying the extension of Q1 and the extension of Q2. Okay? And now if at the end of this link, I place a third prismatic joint which comes out of the plane, I have the 3D gantry structure of the first three prismatic joints. So in fact, there is a clear series. Now first Q1, then Q2, then Q3. In fact, if I'm moving Q3, Q2 and Q1 are not moving. So they are clearly preceding this link in the series. Okay? If I'm moving Q2, Q3 is moving, it's the link connected to Q3 is moving accordingly, but this is not moving. So I can clearly identify from the base to the end effector what is the sequence of prismatic joints. So the answer is that this is a fully serial structure. But congratulations to your colleague who spoke out loud, doing this, proposing a solution. Okay. There's another aspect. Pay attention. This is one case. But of course, I could position this end effector by first moving along the x-axis and then moving along the y-axis. This would be just another sequence, fully feasible. But it's a different robot. So the sequence matters. And For purely combination of prismatic joints, it matters, but up to a certain point. But if you have sequence of revolute joints or sequence of combination of revolute, then prismatic, then again revolute joints, the sequence is fundamental. You may have a complete different mobility if you change the order of the joints beside their type. Okay? So this is gantry robot, is another class of serial manipulator where the first 3 or 2 joints are prismatic, depending if this moves in 3D or only in 2D. And typically, although not exclusively, the last 3 joints are revolute and provide a spherical wrist. Here is another articulated structure, which, pay attention, it has only revolute joints. Okay? But it's kind of strange. It's like a how do we call it? A spider. It's like a spider, like Spider-Man. By the way, it's mounted on the ceiling while it operates downward. Is this a serial or a parallel kinematic structure? Only revolute joints. Well, this is a fully parallel structure. In fact, we will see now a video showing the mobility, but the 6 joints are all placed, 6 actuated joints are all placed in the white box on top. So there are 6 motors, each of which changes the angle of the first link connected. All the rest is purely passive. There is no motor at all. Here at the elbows, here at the passive joints connecting to the end effector, which is this plate below. Okay, which means that the whole structure may be very light because there are only these wires almost, very thin aluminum type links that needs to be moved with motors that are always suspended. They are carried away or around, suspended within the top box, which is the plate of the structure. It's like you can reverse this and imagine then on the floor, but it's irrelevant. Okay? And in fact, this kind of structure allows very fast pick and place operation. Because I can put huge motors and have a very light structure, so I can have very high acceleration. And since in the pick and place motion I should start from 0, accelerate as fast as possible, and then decelerate as fast as possible to stop in the next position, and do this again and again. So the fact that I need the torque produced by the motor enables to have a very large acceleration because the mass of the structure is very low. It's the winning idea behind this mechanical design. Okay? In fact, where do we imagine that this ABB flex picker is being used? Here are a couple of videos. On the left, hopefully you see something. Almost nothing, so first, almost nothing. Sorry about that, but here you can recognize some discs. So these discs are coming from this direction toward the robot, which is somewhere there. I hope you will see something when it gets in motion. They represent some object to be picked. Okay, so this moves on a conveyor belt, so at constant speed, or at the speed that it's equal for all the object on the conveyor. There is a camera overlooking this conveyor, so it recognizes the object and tells the robot where to go to pick up this and place in a remote position. So this is our first test of that robot, so I will start the video now. can you see from the dark? Yeah, very badly, but still here you see a global view, a side view. So this is the recognition by the camera. The camera is, you can see the camera on top here in front of the system. And you should think that there is some computation related to that, because the camera looks at objects and make frames shot at a given time. In the meantime, those objects are moving with a constant speed. So if I recognize one object at time t0, I should know that this object, after a few tenths of a second, is in a different place. And I should command the robot at some time to go there, to the right place, to pick this object. And if I have a limited amount of time, because there are many objects coming, and I should avoid to let them fall down, namely, I should pick them all, I should also implement an algorithmic strategy that tells which object should I take first, probably the most critical one, taking into account that I need more time to pick an object which is on the side of the conveyor belt than one which is in the middle. So there is some algorithmic idea of which to pick first, once I have recognized that this object should be picked. Okay? And then this is why I have very short time to make image processing, to decide what should I pick first, and then to go and pick it. So the acceleration that I use is large because of the demanding task that I'm asking to this robot. And now the application. The application now, it's a different robot. This was the ABB flex speaker that we have seen in the previous picture. This is an equivalent, you can see very similar kinematics by the Adept. This is the Adept Quattro robot. And here you can understand what this prototype was meant for, namely packing of chocolate boxes. This is a nice situation. It's a Forrest Gump idea. So you have now chocolates coming, and they are of different types, so you have to recognize which chocolate boxes are typically multiple sorts. So you have to recognize which goes in which part. Here you see there are different shapes, and you need to do this very quickly. This application was first developed and went into production, guess where? Switzerland. Okay. In fact, the original design of the flex speaker was made by a group in Lausanne from the École Polytechnique Fédérale. Okay. It may be just by chance, but it's okay. So here we, again, this is not in the class that we are considering, but it was worth looking at this video. By the way, before abandoning forever parallel kinematic robots, there is one limitation. Because now we have seen that they can be very massive, like the Stewart platform with prismatic joints, and carry huge amount of payload, like cockpit of an airplane. Or it may be very lightweight and move at fast acceleration. It seems that these are the best of possible worlds, except for the fact that the direct kinematic is not easy. But there is one limitation, namely that the workspace is very limited. If you count the total length of the link constituting the parallel structure, and you draw the possible workspace and compute the side of this workspace, you will get a smaller workspace than if you're using this total length for building a serial manipulator structure. So the serial manipulator has a large, with the same amount of link length, quote unquote, it has a larger workspace than with parallel kinematics. Inside the smaller workspace, parallel kinematics guarantees a more accurate positioning and probably more speed and or more capability of sustaining payloads. Okay, so this is why mechanical designers have developed these two types of robot mechanisms depending on the application. One may prefer one or the other. But again, except for some pick and place operation in industrial setting where rather now, recently the parallel kinematic is taking the place of the SCARA type robot, but up to a couple of years ago, the serial manipulator was completely dominant. In fact, this is an old slide, a pie, which shows the distribution of the robots by kinematic configuration. And you can see these are data from 2004 and refer to 60,000 articulated robots that were installed at that time. Remember, last year there were 180,000 new manipulators installed. So in 2004 there were 60,000. This gives, again, a measure of how the market is growing. And you can see that 63% of these were of the articulated type. So we're like the Comau or the KUKA robots, serial kinematic structure, maybe with some parallelogram, but equivalent to serial kinematic structure, made of all revolute joints. Okay, this means articulated. This typology is also labeled often anthropomorphic. Why is that? Because these arms are like the human arm, possess only revolute joints, no prismatic joints like our arm, which has no such joints. 15% was of the Cartesian or gantry type. Remember, Cartesian is another equivalent term for gantry robots. Gantry is because usually they're coming from top, but Cartesian is more generic. In fact, the joints move along Cartesian axis. This is when you have prismatic joints at the base. There's another category we will see later on when we classify in detail all robots, which is called cylindric. Cylindric means that you have essentially one revolute joint and then two prismatic joints that go up and down and extend, so that you have the three joints constitute a set of cylindrical coordinates in the 3D space. Okay? And this is a 10%, and then you have a larger percent, 12, of the SCARA type. 4 joints, 1 prismatic, 3 revolute. Okay? So when you're interested in buying a robot, not for your house, but maybe within an industrial project, you have a large variety of possibilities. Of course, you look at the cost, you look at the flexibility of the feature that the robots come with in terms of software, hardware. Of course, some software needs to be developed for the specific application, but at some point you will always be faced with looking at this type of data sheet. This is now in Italian, but of course you can have it in any language. So this is a robot Fanuc, 6 degrees of freedom, and here you can read the main parameters. So number of controlled axes, the third line. So this is articulated, means that all joints are revolute. In fact, there are 6 axes labeled from J1 to J6. The next line says how you can mount this robot. And here it's specified you can mount it only on the floor, a pavimento. There are other robots which are mechanically built so to sustain their own load in any configuration. So you can mount it on the ceiling or on the walls and also on the floor. Okay? In this case, only on the floor. Then here you see 6 data for joint 1 to joint 6, all revolutes. You see the maximum rotation, so the joint range. The first joint can rotate 360 degrees. And the first joint here is the base. Around the vertical axis, this can rotate a full turn, so 360 degrees. Okay? While the other axis may be less or more. For instance, joint axis 2 has a joint range of 135 degrees. Joint 2 is the shoulder. So in this case, it's an axis which is horizontal here. And this can have a variation of maximum 135, because otherwise it will hit, or because this is the limitation of the transmission devices internally to the structure, and so on and so on. It's interesting to see that there's one axis here that has actually joint 4 and joint 6 may rotate twice a full rotation, so 720 degrees. So you may have less or more than a full turn. The next number next to each joint axis indicates the maximum rated speed of that joint. So joint 1 can move as fast as 105 degrees per second. Other joints may typically, the farther joints which move less mass can move faster, 130 degrees per second. The last joint, which is this rolling axis, can go up to 210 degrees per second. Okay. Now this is a very important part. Before leaving this table, I will skip this part which refers to dynamic aspect of the robot. So what is the payload that can be sustained? What is the maximum torque that can be held? And then there are other important things. We will come back to that. For instance, this motor is driven by AC electrical motors. It has a repeatability of plus or minus 0.3 millimeters, so 1/3 of a millimeter. And it has a total weight of 1,210 kilograms, while the payload is 165. This is a typical payload to own weight ratio, so 1/10 of his weight. Why is that? What do you think? Why we have this very poor performing? No? If we compare to our arm weighs, I don't know, 15 kilograms. Certainly it can lift its own weight, and even much more. So why is that? Why do you have this kind of massive construction and such a small payload?
Because the max of the joint, the smallest joint.
The smallest joint?
The smallest joint is the weight part of the robot.
Well, true, if you have a chain of anything, the weakest part dominates the rigidity of the whole. This is true. But here it's more subtle. It's a kind of chicken and egg problem. What comes first? So, in order to be very accurate in positioning, this robot has been designed as being very rigid. And in order to be very rigid, they should be massive. Otherwise, they would vibrate while moving. Especially if you're commanding with large torques that accelerate very fast this structure, then you tend to have vibration induced in the structure, unless you have very massive construction so that the first vibration of resonance is very high and you don't excite it. Remember that no body in nature is perfectly rigid. This is an ideal model. If you excite for sufficiently large command or at high frequency, you will excite some vibration in any mechanical device. You have vibration in cars, you have vibration while listening to records or whatever. Okay? So in order to have this first frequency of vibration very high and not excited while moving fast, we need to add mass. And then what is left is for the payload. Of course, in order to move this mass and have a larger payload, you need more bigger actuators, which increase again the mass. And this is the chicken and egg phenomenon. Okay? So at some point you stop. Okay? Now, if you take with this robot a payload which is not 160 kilograms, but it's 250, what happens? Does it crashes? Well, there are two things that happen. First, if you don't exceed the limit currents in the motor so that protection starts and everything is breaks down. So if you don't exceed this, the robot will continue to operate, but there is no guarantee of obtaining this accuracy and repeatability. So they say if you're using up to 165 kilograms, we guarantee that you have this precision at the end effector. Otherwise not. And the more you exceed, the more you may have errors, and eventually you break down because protection comes in for overheating of motors and so on. Okay? So it's not so dramatic if you exceed by 10 kilograms that everything is lost. Okay? So this is very critical, and this is why in the last generation of robots tends to use different material and different design to make things lighter, although not flexible. Okay, so if you're using, of course, aluminium, you're saving. If you're using carbon fiber, you're saving a lot. And you have very stiff structure, but they cost a lot. So it's a trade-off again of cost and performance. But essentially, you will have now industrial robots like the KUKA IIWA, EVA, which is 25 kilograms, 27 kilograms, that has a payload of 14. And it's fully operative in an industrial setting. Okay? So this is more conventional. Of course, to get high with payload, you will still have this kind of massive construction. Okay? I would like to make a drawing now in order to understand better this idea of joint velocities. So suppose that we have a very simple structure, and we will encounter this structure over and over in our analysis. So we have just a planar two-link arm with two revolute joints whose axes are coming out of this blackboard plane. So this is like my arm constrained to a plane that is moving like this. It may also fold on the other side, but change configuration. This is not relevant. Now suppose that you are imposing a velocity, and now I'm calling it Q1 dot to this joint, and you want to compute the velocity of the end effector when the arm is in this configuration. Pay attention, this is an instantaneous computation. So you are in a certain configuration, you impose a velocity to joint 1, and you want to compute the effect on the end effector. Let's say linear velocity. Now this moves in the plane. So more or less, you can do this computation, graphic computation, the velocity will be orthogonal to the line connecting this joint with the end effector. Okay? Do you agree with this? If this joint is not moving. So you have this configuration, you're moving this shoulder, and so you will have a contribution. Of course, the farthest this away, the same amount of angular velocity of this joint will produce a larger end effector velocity. Okay? Now, suppose that you're moving also the second at the same time. You're given some velocity. Now, the same holds true. So this will be along the normal to the connecting link, which is the second link. So you will have a velocity of this kind. Now, if you're putting both commands together, you will have the sum of the effect. Okay? So you will have, here you can build a parallelogram, and then the sum of these two vectors, this will be the resulting V. Okay? And this computation is called direct differential kinematics. Okay? So, in a given configuration, I assign joint velocity and I compute the velocity of the end effector. Now I've done a graphic computation, but this can be transferred in a numerical way. Of course, there will be an inverse differential kinematic. Who can guess what is the inverse differential kinematic problem? Exactly. No? I'm given a desired velocity here, and I want to compute the two velocity here that realize in this configuration that instantaneous velocity. Remember, instantaneous, because once you apply this velocity, the configuration of the arm changes and you have a new problem. So this is just at some instant. Now, when I look at this, why I'm drawing these things? Because when I look at this maximum speed of the joint, I still have no idea, in principle, of what is the maximum velocity that I can achieve with the end effector. Why? Because this will depend on the actual configuration of the robot. If I'm firing all motors at maximum speed, the speed of the end effector, the velocity of the end effector, will change depending on the configuration of the arm. We want to do a very simple example to convince ourselves about this. Okay, let's take this robot and put some number. Let's put it in a very easy configuration. Suppose that this is straightened like this. And suppose that this velocity is 1 radian per second, and this velocity is 1 radian per second, and this link is 1 meter long, and this second link is same 1 meter long. Question: what will be the velocity of the end effector? Well, we do exactly the same computation. Now we have numbers. Okay, so let's look at the contribution of this velocity. This is 1 radian per second at the distance of 2 meters. It will give here 2 meters per second speed. This velocity. Okay? Angular velocity times distance. And it's in this direction because it's the normal to the to the segment between these 2 points. Okay? Now, there's another velocity here, which gives another contribution, which will be added in a vector form. Added like we are adding this vector. But this gives exactly the same direction, and it's a 1 radian per second at a distance of 1 meter. So this will be 1 meter per second speed in the same direction. So when we are summing things, we'll have 3 meters per second. Okay? Now, suppose that 1 radian per second, namely 57 degrees per second, was the maximum speed of this joint. Well, the guess is that this is actually the maximum speed that we can reach for the end effector, because we are at the extreme of the workspace, close to the boundary, and this is the maximum contribution that we have. But if we apply the same speed of the joint, so 1 radian per second and 1 radian per second, in a different configuration, for instance, this configuration, where the first link is, again, horizontal, and the second link is completely folded on the first one. So, and since the two lengths are the same, it's like being in this configuration. And now I'm giving the same speed to the joint. Now, if I'm giving 1 radian per second to this joint, what will be the end effector velocity? 0. No contribution, because I'm folded like this. I'm moving the first joint, but the end effector is not moving. It's changing orientation, but now I'm considering only the linear velocity. Okay? So this, you can put it or you can leave it, will give 0 velocity. Now, what about the 1 radian per second of the second joint? What will be its contribution to the end effector velocity? This is, again, 1 meter distance. So 1 times 1, 1 meter per second. In which direction? Going down. So this will be 1 meter per second in the opposite direction of this. So you can see that changing the configuration, these are two extreme cases, the same velocity that we are commanding to the joint will generate two different velocities, one very large, one medium, in two opposite directions. Wow. So if I'm in a generic configuration, not as easy as this, which can be figured out very easily. I'm in a generic configuration with a 7 degree of freedom robot, and I'm giving generic velocity to each joint. The computation should be organized so that I get the solution in a clear form, not just going graphically like this. Okay? And this solution will be the Jacobian. But at this point, we'll make use of the so-called Jacobian matrix, which changes with the configuration. Exactly while the result changes here, not because we are changing the joint velocity, but just because we are changing the configuration. Okay? Now we will come back to this differential kinematics, direct and inverse, but for the time being, the presence of this maximum value is just a generic indication of how fast you can go with your end effector. Okay? Just this was my warning. The number of joints of frames. So I've not yet talked about frames, but since probably you're looking ahead, the number of joints will give us the number of frames that we have to define for the structure, one for each link. Remember, the frames by which we characterize the position and orientation of each body of the structure are associated to the links. So if we have 6 joints, we will have 6 moving links, and on each link there is a reference frame. Okay? So there will be 6 reference frames, and we should characterize their position and orientation with respect to a basis 1, which is at the link 0, let's say, the floor, which is not moving. It's the reference frame that we have mentioned before. So, in fact, if you have a robot with n joints, you have n plus 1 bodies. The base body 0, which is not moving, and the n bodies which are moving, one each after the associated joint. So we will have n plus 1 frames, and we will characterize the relative position of this n moving frame with respect to the n plus 1, the 0th frame, which is at the base. Okay, this is forward-looking toward a systematic way of describing kinematics. Okay? Good. So another things that we can do, and you can find in the data sheet, is pictures like this, which characterize the workspace of this robot. And this is our just side view or top view projection of an object which is three-dimensional, which is the collection of all points that can be reached by the end effector. Okay? And you can see that, of course, this will be limited from the base, so you cannot go there because your links are not long enough. But the nice thing, the critical thing, is that you will find some holes within the natural, this hyperbole that you have there. Okay, why do you have holes? Exactly because you have limits for the joint ranges so that you cannot access some internal point. And for the same reason, you try to eliminate mechanical stops in order not to have inside the workspace hole that you cannot reach. Now, imagine that you have to pick something here and place it there. Can you go in straight line along a Cartesian path? No. No, because at some point you need to exit the workspace. Of course, you can take this object, rotate, and bring it on the other side. But this will be no linear path. Okay, so it's a different story. Okay? However, if you want to go from one point here to one point which is on top of the workspace there, and if the connecting line is all inside this workspace, then you can do the motion in straight line. Okay? So it's very important to characterize the workspace in order to understand what is the actual mobility of the robot, taking into account the kinematic architecture, so the link length, but also the joint limits. Okay? Now, it's very difficult to figure out the workspace of a robot in general. You should imagine how do you use this section of the workspace? Well, essentially, in this case, the joint base can rotate 360 degrees. So you take this section, you rotate it in space around the vertical axis, and you generate a solid object, which is the workspace. Okay? In general, it's kind of hard, if you move out of the plane, to characterize completely and geometrically in an intuitive way the workspace. So you need some way of checking if the point is inside the workspace or not. And for doing this check, you use the direct kinematics and the inverse kinematics. Okay? So again, the model is for solving very practical problem. Or to visualize workspace, you can do a simulation. You can do a simulation, a graphical simulation in which you describe the various links and how they move with respect to the previous one, and we will use a standard formalism which is called Dennavit-Hartenberg convention, so a way to describe any serial kinematic chain, no matter if the sequence, which sequence of joint you have, no matter which length you have, no matter how the joint axes are placed in space. So it's a general way to characterizing any direct kinematics. And then you represent the solid links and you connect this through frames and you use some standard package. This is a a video that described the mobility of this Comau robot. And of course, you don't visualize the workspace, but you see what the robot can do by moving one joint at a time, by combining the motion of the joints so that the end effector moves in a linear path, and things like that. You can see the folding of the robot. Now it's moving along a straight line, now going up. You see that for going up, you move simultaneously all the joints. It should be a coordinated motion of these joints. Okay. Or you can use, I found this on the web, I don't remember even where. Well, we did this using the freeware software VREP. And this is the KUKA that we have in the lab. Again, you can recognize here 7 joints, 1 rotation around this base, 1 rotation around this axis, 1 rotation around this axis, another along this axis, another around this. The silver ball is rotating with respect to the orange. And then finally, a rotation of the last flange, on top of which you can mount a force sensor, a tool, a gripper, whatever you wish. Okay? So there are 7 joint axes. You see that this structure is also pretty modular, because this is reproduced several times. Only the single parts are quite the same. And in fact, all the electronics is on board, so there are very nice features for this robot, but now we don't care about this. We care only about the kinematics and looking at the mobility of this robot. And we can do a simulation, for instance, in MATLAB or in Simulink, and then obtain a story of the joint angle and feed into the visualizer only, the VREP, these angles in time, and we will see a motion in the 3D space. Okay, so from a very difficult to understand object, which are the profile of the joint motion in time of each joint, we will have something which we understand if the robot is doing what we expect or not. And this is the video. You see, it starts, this straight position is the so-called home position, is the 0 configuration situation. And here you see that all the joints are simultaneously moving until it goes back to the same initial point. You can see it once more. See how natural the motion happens to be when we are moving all the joints simultaneously. We are not doing like robots in ancient time, moving one joint, second joint, third joint, and so on. It's all smooth, coordinated motion. Okay? So we're almost done. Going slower than expected, but I hope you don't mind. So in this picture, you may see, again, all the possible things that you can mount on the end effector of a robot. This is a very extreme situation. You recognize in orange the robot here, and here is the end effector. And from this position to here, you have only additional equipment. So you have an end effector like this, however, which is composed of several things. First of all, you can mount a first cylinder, which is a force torque sensor. So it's an object that is able to measure the forces and the moments applied to this object with respect to the holding part, which is the end effector of the robot. Okay? So if you press or if you pull down, you will sense a force in this direction. If you push on the side, you will sense a force in this direction. On the other side, and so on. So in fact, if you apply 2 forces and you try to rotate this object around the 3 axes, you measure moments. So this is a so-called 6D force torque sensor because it's able to measure all these quantities. And this is of paramount importance when you're getting in contact with the environment and you want to be sure that you're not applying too much force on the environment. Okay? Then, under this, you have another object which is now not very clear, which is a pneumatic tool exchanger. So it's an object that enables to change tool on the fly. So you have a raster of end effectors, grippers, tools, and the robot is able to go there, relax the current tool, and exchange tool with just a pressure or a magnetic connection, so that the whole process can be performed automatically without intervention of a human that is changing the end effect. Okay? On the side here of this structure, you see a camera. Just read the camera, probably. And the camera is mounted in the so-called eye-in-hand configuration. So the camera is moving together with the end effector of the robot. So it's carried around by the robot itself, which makes a bit more complicated the processing of the images from the camera, because every time the robot is moving, the same view is changing. And we should be able to compute the kinematic transformation associated to this, because the camera carries a known reference frame with one axis along the image axis of the camera, of the lens itself, and whatever I see with respect to the world depends on how I'm positioning and orienting the camera with the robot. Okay? On the other hand, it's very convenient to have an eye-in-hand situation, because if I'm grasping something, I will get closer and my camera will continuously view the object so that I can be very precise, driven by the sensor, by the camera sensor. If I have a camera overlooking the object, the scene, and I'm going with my robot to grasp the object, at some point the robot will occlude the visibility to the camera, and I'm going open loop. Okay? So there are advantages and disadvantages. Finally, here at the bottom you can recognize quite a sophisticated gripper. In fact, it's almost a dexterous hand. It has 3 fingers, but these 3 fingers in this case, they move in a coordinate way. I cannot move only one finger. I can only open or close all the 3 together. So this is why it's classified as a conventional gripper and not as a dexterous robotic hand with 3 fingers. If I could move the 3 fingers separately and independently, then this would be a simplified human hand or robotic hand. Okay, but this is still a gripper. So you can see that you can mount a lot of things. Remember that all that you have beyond the last flange of the robot itself, it's a payload for the robot. So not the things that we are going to grasp with this object will wait, but the 3 finger, the tool exchanger, the force sensor, and whatever you have, it's all part of the payload. So if you have a payload for a small robot of 6 kilograms, and you're using 3.5 kilogram only for these devices, you're left with 2.5 kilogram to useful payload. So take this into account. Okay, I think we can stop here, and we will resume with few slides from here on Friday, and then we will move to the next group of slides. Remember, those who have not sent me the email, please do so, because I'm now merging the lists.